Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of Energy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the 8th one. This lesson is divided into several parts. Let's start by applying the rate equations for conduction and convection to the fin. For any boundary condition, after obtaining the temperature distribution, we can find the curve derivative and apply the Fourier's law to calculate the heat transfer rate at any point in the fin. What is the expression for the heat transfer rate for a very long fin? Let's use this very simple mathematical model to learn how to obtain the heat transfer rate of the fin. First, we find the derivative of theta and its value at x equal to 0. Then, we apply the Fourier's law. Substituting mf by its expression, we obtain the expression of the heat transfer at the base for a very long fin. Notice that although the fin can be theoretically infinite, the heat transfer rate is finite. Let's now calculate the heat transfer rate using the Newton's law. We need to define a differential control volume of length dx. The area of contact with the fluid is the perimeter times differential of x. Applying Newton's law, the heat transfer rate is equal to the product of h, p, theta, and differential of x. The fin heat transfer rate is the integration of dq from x equal to 0 to x equal to Lf. For a very long fin, we substitute theta by its expression. H, p, and theta 0 are constant, then we can integrate the exponential. Developing this equation, and taking into account that Lf tends to infinity, we arrive to the expression of Qf after the integration of the Newton's law. Recall the definition of parameter m. Arranging terms, the equation obtained as result of the integration of Newton's law is the same that the one obtained applying the Fourier's law in the base of the fin. This is also true for case A, fin with convective tip, and case B, fin with adiabatic tip. However, it is not for case C, a fin with prescribed temperature at the tip. Let's study the heat transfer rate for case C. It represents an extended surface between two solid bodies. It is like a thermal bridge. The temperature distribution depends on the values of T0, TL, and the fluid temperature. It also depends on the parameter m and the fin length. The heat transferred to the fluid is the sum of the heat that reactives the fin by conduction in both extremes. Q0 is found applying Fourier's law. Qf can be found integrating the Newton's law. For calculating QL, we must apply again the Fourier's law. Notice that QL goes in the direction of decreasing x. Therefore, must be multiplied by -1. The conservation equation in this kind of fin can be also written with all the conduction terms in the direction of x. Therefore, the way you write QL depends on how you has written the conservation equation. What is the expression for the heat transfer rate for different boundary conditions? The heat transfer rate between the fin and the surrounding fluid can be calculated for each boundary condition after knowing the excess temperature function. In this video, we have developed the expression of the heat transfer rate at the base for case D. You can do the same for an adiabatic tip fin. The uppercase M, which is the result for case D, is the reference value for other boundary conditions. For case B, the hyperbolic tangent approaches 1 as Lf approaches infinity, and Q0 tends to m. For case C, the heat transfer rate for x equal to 0 depends on the temperature at the tip. The more complex expression is the one for case A, the tip with convection at the tip. We can also use the Newton's law in the interface of the fin and the fluid, and integrate it through the fin surface. For a very long fin, an adiabatic tip fin, and a tip with convection at the tip, the application of the Fourier's law at the base and the integration of the Newton's law give the same result. Notice that for case A the heat transfer rate at the tip must be added. For case C, as discussed before, QL must be included in the overall heat balance. How the conduction heat transfer rate can be calculated at any cross-section of the fin. It can be also useful to have the expressions for the heat transfer rate by conduction at any section of the fin. Like we did for the base, we can apply Fourier's law at any point along the fin. These expressions can be useful to you for solving fins exercises. Note that the conservation equation must always hold. At any point, the heat by conduction at the base is equal to the heat lost by convection plus the heat that continues by conduction to the tip.